Hello, this is section 2.6 for Calc AB, and today we're going to be talking about derivatives of inverse functions. And the notes actually start off, the first page and a half is just a review of inverse functions. If you don't understand inverse functions, it's going to be challenging to try to figure out the derivatives. So this first part deals with the definition of an inverse function, and it says if you have an inverse, then when you do the composite, so f of g of x, given g is the inverse of f, it's going to spit out x. And if you do the vice versa, g of f of x, it'll also spit out x. And that's a good test to see if two functions are in fact inverses of each other. So that's what we're demonstrating on this first one. So we have two potential functions. So we plug g of x into f of x, and we see that you get x, and then vice versa. And you also get x. Yes, they're inverses of each other, right? Now, in this box, just a quick little review. So g is the inverse of f is the inverse of g, okay? And the domain of your inverse is equal to the range of your function, and vice versa. And that's big. That's a huge one. And that also can get a little confusing. A function need not have an inverse, but if it does, the inverse is unique, and the inverse is a reflection of the graph over the line y equals x. And a good way, sometimes it's hard to see what the reflection looks like, so you can always fold your paper to see what it would look like if you do the reflection. All right, then this is another thing about how if you have AB on the function, then the ordered pair BA would be on the inverse, so it does flip, but that can get a little confusing. We're going to use that later on in the notes. And then lastly, to have an inverse, the function needs to, of course, pass the vertical line test, but it also needs to pass the horizontal line test. And to pass that horizontal line test, it's going to have to be increasing or decreasing over the entire domain, and we call that strictly monotonic, and that's what this is referring to. So you can see this goes from increasing to decreasing. It's going to fail the horizontal line test, whereas this one is always increasing and it passes the horizontal line test. And then this last one, you have this little section right here. Since it fails the horizontal line test, it does not have an inverse. Now you might say, Cogswell, there's a parabola here, and we did a parabola just a little bit ago. And I agree, but notice the parabola has a restricted domain of x greater than or equal to 0, so that's only the right half of our parabola, and if you're restricting the domain, then it actually passes the horizontal line test. So now, which of the functions have an inverse? So with these, most of these you'll know the parent graphs, so you'll be able to quickly sketch them. But if it's one that you don't know the parent graph, then use your graphing calculator or think through it. Could you plug an x in and get two y's out of it type deal, or vice versa? But yeah, okay. But we graphed this one, and we'll graph this one in class. All right, now guidelines for finding the inverse. So first determine if it has one. Don't want to waste your time. Then solve for x as a function of y. So remember, you flipped the variables. That's what we're doing here. We flipped the variables, and then we solved for y. And when you take the square root of both sides, don't forget that plus or minus. Now, with this, you're only going to keep the positive, because we're only going to keep the top half of this equation. And then when you go to write your answer, you can see that this is a perfect example of the function has a restricted domain that's greater than or equal to 2. And when you graph this, there's actually another part to this equation that we don't include. It's this part. So since we're restricting the domain, it's just this half. And you'll notice that x greater than or equal to 2, that now becomes the range of your inverse. Oh. And then that helps you because we knew that our function, the y was greater than or equal to 0, that now becomes the domain of your inverse function, x greater than or equal to 0. So that can help you when you're going to try to figure out, well, this now is the range, and that might help you figure out the domain of your inverse. They flip. And I show you that later in the notes. All right. So now we're ready for derivatives. Now that we've reviewed inverse functions and hopefully, and if you have any questions, email me and let me know. If there's something you don't remember or you need help with, let me know. So now we're ready to discuss continuity and differentiability of inverse functions. So first, if a function's continuous on the domain, then the inverse will be continuous. All right. If the function is increasing on the domain, the inverse is increasing. That's something you might not have ever thought about, and you can see that here. Your function's increasing, and so happens to be your inverse, and then vice versa as well with decreasing. Now this one's interesting. If f is differentiable on an interval containing c and the derivative does not equal 0, then the inverse is differentiable at c. But more importantly, if the derivative equals 0, the slope is 0, and the horizontal tangent, you have a horizontal tangent, that would mean the inverse has a vertical tangent at c, and the inverse would not be differentiable there. So I'm going to scroll back up and we're going to look at this graph. And you can see right here where on the original function you have a horizontal tangent right there. And when you look at the inverse, you can see that, oh, that corresponding point, it turned into a vertical tangent. Oh. And that's a hint to when you have your slope of the tangent line on your function, it becomes the reciprocal on your inverse. But that becomes a problem when it's a horizontal tangent that then turns into a vertical tangent. So you have to be a little bit careful there. All right, so that's what we demonstrate in these next two examples are you have inverse functions, you do the derivative, and when you find the slopes of the tangent lines on the function, you get 3, 12, and 27. So we're plugging these x values into the derivative of the function. But notice it's the corresponding points for your inverse. You see how it's the same AB, but it turns into BA. So corresponding points. And when you plug these x values into your inverse derivative, you can see that the slopes are reciprocals of each other. Right? And then we did that again down here. So with this one, we talk again about, we sketch the graph, and you can see the domain of your function. That's what's in blue. The domain is from 0 to infinity. That was given to us right here. But that's the range of your inverse. And when you're doing the range, I always like to go from bottom up, and that's the red. So you're including 0 and going off to infinity. Then the domain of your inverse is the range of your function. So when you're doing the range again, bottom up, you're not quite getting to 0, but you're stopping when you get to 1 and you get to include it, and that becomes the domain of your inverse. So when you're doing domain, I always go from left to right. We're not quite getting to 0. I'm looking at the red function, but we get to stop at 1 and include it. So that's a good visual of how it flips. Then here's the calculus. So show that the slopes of the graphs of our function inverse are reciprocal. So we used our calculator in class. So we had the calculator find the numerical derivative of our function at 1, which is where we got -1/2, and then we used the calculator again to get the numerical derivative of our inverse at 1/2. And we were able to see that, yeah, they're reciprocals of each other. So I definitely use your calculator and see if you can get the numerical derivative and get that to work on your calculator. All right, so here comes a very helpful formula, and this is the derivative of an inverse function. And we've already seen this. We've seen this happen. If you have the derivative of your inverse, it's the reciprocal of the derivative of your original function. And that's what this formula is trying to tell you. Same thing here. Now, I find these two formulas a little bit confusing. So I have one that I prefer this way I never screw it up, but you have to be a little careful. So this is Cogswell's formula. And what it is, it's the derivative of our inverse. So it actually starts off exactly the same. And then I just simply write equals 1 over the derivative of our function. But there's a big but there. This x is the x of your inverse. And that's what I wrote down here. This x is the x of your function. So you'll have to be careful. These x's represent two different values. But the x that it's with, that's the x of the inverse, and this is the x of the function. So it's pretty easy to remember, and it's a lot easier to remember than this mess, in my opinion. Okay? So that's what I'm demonstrating here. We found the derivative of the function, plugged in -2, and got the slope. Okay. Then we found the derivative of the inverse, plugged in -16. That's the remember these are the corresponding points. Plugged in -16 into the derivative, and it got 1/24. Okay. So yeah, that just confirms what we already knew. The slopes are reciprocals at the corresponding points. But here's where we can use this shortcut. So this is just me showing you that the shortcut works. So I claim we never had to do this step right here. We could have just crossed this off, because once we got the derivative of our function, well, the derivative of the inverse is just simply 1 over the derivative of our function at -2, which is 1/24. And look, see how you got the same thing? So we could have just gotten this answer and used the formula to just say, okay, well then the other derivative has to be 1/24 and be done. Now, the last example is where, I'm going to put myself over here, is where you have to use the formula. And this is why it's really beneficial. So in this case, the first part's actually review. So what is the value of the inverse of x when x equals 12? And this x is the x of the inverse. So I wrote that here. Inverse of 12 equals... So you'll say, okay, I'm going to plug 12 into the inverse function. Well, you have a problem. Can you find the inverse of this function? Can you flip the variables and solve for y? And the answer is no. You can't. You can't find the inverse. So we said, all right, well, if this is the x value of the inverse, it must be the y value of your function. So now I can set the original function equal to 12, and that's doable. We used our calculator to solve. And we got x equals 2. And then if that's x equals 2, that must be the y value of your inverse. So we had to be a little bit clever there because we couldn't find the inverse. And we have to do the same thing for the derivative. If we can't find the derivative, or excuse me, if you can't find the inverse, how are you going to find the derivative? But we don't have to, because if we can do the derivative of our function and plug in 2, then that's going to be the inverse derivative at 12, well, the reciprocal. So that's how we're getting that answer. So we were actually able to get the derivative of our inverse without ever having to find the inverse. That's the cool thing. But you will need to practice this, right? Now, day 2. I don't know what's going on there. So for this one, this whole first section is just review with inverse functions. So watch, let me move myself over here. Watch this YouTube video to refresh your memory on these domain and ranges, and just make sure you watch your intervals when you answer. Your calculators are programmed intervals, so you'll need to be careful there. All right, and let me know if you need help. There's a lot of YouTube videos. Just search inverse trig functions to refresh your memory. Okay. Now, the derivatives of inverse trig functions are not bad. And even though it looks complicated, they actually come in pairs. So if you look arc cosine of u, it's the same derivative for arc sine of u, excuse me, is the same as arc cosine. It's just negated. So even though it looks hard, you really only have 3 to memorize. Just remember what pairs and to negate the correct ones. Okay. Now, but it's just chain rule. Arc sine is 1 over the square root of 1 minus u squared, then times the derivative of the inside. That's that u prime. Okay. So when you're doing these, so the derivative of arc sine is 1 over the square root of 1 minus u squared, which is what's here, then times the derivative of the inside. That t squared turns into 2t. So then we just reduced it. Same thing over here. Arc cotangent is -1 over 1 plus u squared times the derivative of the inside. So there's your e to the x over 3. But then you have to do another chain rule, times 1/3. And then once you get the derivatives, then you just maybe clean it up a little bit, but that's all. Now for this one, arc cosine is just -1 over the square root of 1 minus u or x squared. The derivative of the inside is 1 for that. minus, and then you had to do the product rule on this. And this, when you factor out and simplify, it ends up reducing beautifully. Okay. And then this is just another one to walk through the steps. Let me know if you have questions. Okay, please do your homework.